LLMs struggle with factual consistency and complex relational queries. Standard retrieval augmented generation often fails on multi-hop questions. RAG relies on flat text chunks, losing critical structural context. GraphRAG solves this by leveraging structured knowledge graphs. We move beyond simple vector similarity search limitations. The core problem is maintaining entity relationships during retrieval. Graph structures inherently preserve these complex connections. This integration drastically reduces LLM hallucination rates. We will detail the exact pipeline for implementing GraphRAG today. This approach is essential for enterprise knowledge bases. The GraphRAG pipeline starts with source document ingestion. Entities and relationships are extracted using specialized natural language processing models. These triplets form the foundation of the knowledge graph, KG. The KG is stored in a native graph database like Neo4j or Janus Graph. This structure provides explicit semantic paths between data points. The LLM acts as the final reasoning layer, not the primary knowledge source. Retrieval involves querying the graph first, then passing the results to the LLM. This hybrid architecture combines semantic search with structural integrity. We use cipher or gremlin queries generated dynamically. Entity extraction requires high-precision named entity recognition models. Relationship extraction uses open information extraction or trained relation classifiers. For example, extracting Company A acquired Company B in 2023. This yields the triplet Company A acquired Company B. Schema definition is critical before ingestion. Define node types like person, organization, and event explicitly. Define edge types like works for or located in precisely. Automated schema generation often requires human review for quality assurance. Use tools like Spicy or custom transformer models for extraction. Data cleaning and deduplication are mandatory steps before graph population. Graph indexing involves creating vector representations of nodes and edges. This allows the LLM to understand graph proximity numerically. We use algorithms like Node-to-Vec or Graph Attention Networks, GATs. Node-to-Vec generates embeddings based on random walks across the graph structure. GATs incorporate neighbor features during the embedding process. These embeddings are stored in a vector index alongside the graph database. Retrieval queries use vector similarity to find relevant starting nodes. This hybrid indexing supports both structural and semantic search simultaneously. The embedding dimension significantly impacts retrieval performance. Higher dimensions capture more nuance but increase computational cost. Subgraph retrieval focuses on finding localized, relevant context efficiently. The user query is first mapped to specific entities in the knowledge graph. This entity mapping uses techniques like entity linking or fuzzy matching. Once entities are identified, we traverse the graph outwards. A common strategy is the k-hop expansion, typically k equals 2 or 3. This limits the retrieved context size, preventing prompt overflow issues. The resulting subgraph is serialized into a structured text format. This format, often Turtle or JSON LD, is then injected into the LLM prompt. Efficient subgraph extraction minimizes latency during the RAG cycle. Multi-hop reasoning addresses complex questions requiring multiple steps. For example, who manages the team that developed product X? This requires traversing multiple relationships sequentially. The system dynamically generates a sequence of graph queries. The output of the first query informs the parameters of the second query. This iterative querying mimics human deductive reasoning. We use specialized LLMs fine-tuned for cipher generation from natural language. This is often called text-to-graph query translation. Error handling for failed query generation is a significant implementation hurdle. Ensure the generated query adheres strictly to the defined graph schema. The retrieved subgraph context must be presented clearly to the LLM. Prompt engineering involves structuring the serialized graph data effectively. Use clear delimiters to separate the context from the user query and instructions. Instruct the LLM explicitly to base its answer only on the provided graph context. This constraint is vital for minimizing factual errors. We use few-shot examples demonstrating desired output formats precisely. Temperature settings should be low, typically 0.1 to 0.3, prioritizing factual accuracy over creativity. Monitor token usage carefully, as graph serialization can consume significant context window space. Evaluating GraphRAG requires specific metrics beyond standard RAG evaluation. Focus on structural accuracy, how often the retrieved subgraph is complete and correct. Use metrics like F1 score on relationship extraction and path completeness. Latency is a major hurdle, especially during complex multi-hop retrieval. Optimizing graph traversal algorithms is essential for production systems. Maintaining schema consistency across evolving data sources presents a continuous challenge. Scaling the graph embedding process for massive KGs requires distributed computing frameworks. Current research focuses on optimizing the text-to-graph query translation accuracy.